Hello wonderful person, this is Anton, and in today's video we're going to be talking about the smallest black hole we've discovered. Specifically about a black hole that is essentially at the limit of how small black holes can get. And we're going to put it in our solar system and find out how small it really is. Welcome to What the Math. So what you're looking at right now is actually a real-time representation of what one of the smallest black holes in our galaxy looks like. I'm going to change color scheme a little bit just so you can see that it's also very, very bright. Now, I'm sorry for those of you who might be photosensitive, but basically what you're seeing here is a tremendously powerful but also very, very small black hole that is generating such a huge energy here by essentially vibrating and by essentially spinning the accretion disk around it ridiculously fast. And what it does is it produces what's known as QPO, also known as quasi-periodic oscillations. Now you can actually see them from this distance. If I dim this a little bit, you see how it starts vibrating just a little bit. It's actually really fast, and this is what we can use in astronomy to actually detect the mass and, in essence, the size of a black hole. The faster it vibrates, the faster this QPO is in terms of frequency, the smaller the black hole. And this is essentially how we discovered one of the smallest black holes ever discovered, and possibly even the smallest, known as XTE J1650-500. This is actually not it. This is this particular black hole is something I've talked about previously. Is kind of we're not really sure what it is. We don't even know if it's a black hole because the recent estimates for its mass show that it's about 2.1 masses of Sun, and this means that it might not be a black hole. We might have been just actually wrong about this. This is an object known as GRO J0422 plus 32. We're going to take a look at another one here. The object by the name of XT J1650-500. This is actually a black hole for sure. As a matter of fact, it's a black hole that has a companion, and they obviously orbit around one another. So here you can actually see both of them. If we accelerate time a little bit, you'll see how they start moving around each other and create quite an interesting dance. Now, the interesting thing about this particular black hole is that we've measured this particular object, which is actually right here, quite precisely. We know that its mass is approximately 3.8 masses of the Sun, and we know that its size is about 24 kilometers in diameter. Although in the game right now it's about 23. That's maybe a little bit off. We also know that this particular black hole is definitely one of the smallest in terms of limits, and it's actually very close to the theoretical limit of the mass, which is about 2.7, but we still haven't really confirmed it because we haven't found enough black holes to estimate this limit. In theory though, at 2.7 to 2.8 masses, a black hole should really be a neutron star, not a black hole. So what I wanted to do in this video actually is to put this thing into our solar system and compare its size to other objects in our solar system just to demonstrate how tiny it really is. And we're going to do this by going to our own solar system in Universe Notebook Square and place this unusually small but very massive black hole right here in the orbit of Jupiter around one of its moons, around Io. I thought it was a cool moon to add a black hole to, so I decided to add it right here. And as you can kind of see, in terms of size, it's actually not that big at all. It's actually really small. And it already started breaking something apart as soon as I placed it. Now let's actually compare it to other objects in our solar system by going to charts and selecting things by radius. And obviously the most large in terms of size is Jupiter. Then as we start going down the list, we'll discover where Earth is. And eventually we'll start hitting things like dwarf planets, planemos, and eventually asteroids. And as you can probably guess, we have to go down the list quite a lot before we find this black hole. As a matter of fact, as I keep scrolling down the list here, there it is. It is actually no larger than a relatively small sized asteroid. So it's right here between two, I think these are actually moons. One of them is a moon at least, Ananke, and what's the other one called? Adrastea. So both of these are moons. And this is about 8 kilometers in radius, this is about 14, and right between them is XTE J1650-500. But it's also in the list of asteroids, so some of these are actually asteroids. Now, this is very, very interesting because this thing, only being the size of an asteroid, possesses more mass than the entire solar system altogether. And you'll witness this in a few seconds as soon as I basically zoom into Jupiter right here and let go of my pause button, because right now the game is actually paused. And as soon as we do this, you'll see that this unusually massive black hole is going to start destroying things really, really fast. This is actually almost in real time. Let me just see. Yeah, this is maybe 8 times quicker than real time, 8 seconds per second. So it destroyed Io really, really quick. Io is gone. The next on the list is, well, it's actually Jupiter. Even though Jupiter is so massive, it's most likely not going to survive for very long against this unusually massive black hole. Now, I know it's a little bit dark here, but if I move from this angle, you'll see that things will start moving toward this black hole pretty quickly. There's that Adrastea we saw a few seconds ago. It's moving toward the object at several thousand kilometers per second. Jupiter is doing the same thing. It's already at 1,000 kilometers per second. And as you can see, the tidal effects of this tiny black hole start breaking it apart pretty quickly. It only took just under a minute for Jupiter to move several thousand kilometers toward the black hole and basically get completely sucked into it. And so the entire solar system is actually going to follow Jupiter, and it's most likely going to basically get absorbed by this black hole. And you'll notice that pretty much everything is going to start moving toward the black hole in the next few minutes. You can kind of see by the vectors of velocity where things are moving. Some of the things are not being absorbed, they actually get thrown out because they actually pass by just a little bit off where the black hole is. And so this gives them a huge boost, huge slingshot to basically escape the solar system now. So Metis, for example, is now most likely going to escape, and so are these guys here, moving at like 3,000 kilometers per second. So let's accelerate this just a little bit to see what this super tiny black hole causes and what it actually creates in our solar system. And here, with orbits enabled, it's actually kind of cool to see how pretty much everything in our solar system starts changing orbits really, really quickly. And as you can see, it sort of starts doing so much math that my computer can barely handle it. I'm going to have to decelerate the game just a little bit as it sort of recalculates all of the orbits in our solar system, and pretty much everything assumes an orbit around this black hole. It's now pretty much the center of the solar system. So even the sun is actually in orbit around this black hole. And some things here have a very, very elliptical orbit. Some things kind of start getting orbits that take them outside of the solar system. And all of this is due to the fact that even though it's so tiny, only about 11 kilometers in radius, which is maybe the size of a really large city on Earth, the mass here is 3.8 times the mass of the sun, and essentially the mass of the total entire solar system, because sun basically possesses about 99% of the mass in our solar system. So after only a few months, pretty much everything here will be in orbit, but I really want to see what happens to our sun actually, because it does seem like it's actually accelerating towards the black hole. And if it comes close enough to the black hole, it might actually get shredded apart and create a very, very large accretion disk and tons of energy around this black hole. So let's see if it actually happens, because I think it is moving there. Yeah, it's definitely moving toward the black hole. As a matter of fact, it's moving really, really fast toward the black hole, as I just realized. So I might need to decelerate time just a little bit so we can see all of this happen in real time. Here comes the sun. Very quickly, And this is going to be absolutely gorgeous to see how this black hole shreds the sun apart into tiny little pieces. And we've actually observed this at least once in real life, when a star approached the black hole relatively close and basically ended up getting shredded apart. And this tiny little speck is going to basically cause the destruction of our solar system. And here we go. We're right inside of it, and now basically there's nothing else left. Well, that's kind of it. That's really all I wanted to do in this video. I didn't really expect to destroy the solar system in such a spectacular manner, but it happened. At least we created a very large accretion disk, lots and lots of energy here, and tremendous amount of X-rays and all kinds of other radiation being emitted by this beautiful black hole. Hello wonderful person, this is Anton, and today we're going to be going to our central black hole known as Sagittarius A Star, and we're going to take a look at one of the most famous stars orbiting around it, and find out if we could potentially have a habitable world similar to our planet Earth orbiting around that star. Alright, so we're going to be moving away from planet Earth, and now we're going to be looking at the center of our galaxy. Let's actually look at it from this distance first, because I would like to actually show you what we know about it and how we kind of discovered a lot of things about it as well. If you type Sagittarius A in Space Engine, you'll see that right in the middle of the Milky Way, right there is actually something unusual going on. As a matter of fact, you can even see what's happening there if you zoom in close enough. Now, this is what and how the scientists discovered that there was a central black hole in our galaxy, because they saw the unusual motion of stars. I've talked about this in one of our previous videos, so we're not going to cover this in too much detail right now. But basically, the idea here is that there is actually, or there are a few stars that orbit really close to Sagittarius A Star, and you can see them if you accelerate time enough, and accelerate time enough to actually start seeing the motion of objects here. Now what you're seeing is basically a bunch of stars orbiting around the central region here, and there's one star in particular known as S2 that we've studied quite profoundly. It was originally discovered back in 2002, and since then we've actually seen it orbit once around this region, and so we were able to establish both its potential mass and also its orbital parameters very accurately. And you can actually read more about this star just on Wikipedia, actually, by going right here to the S2 star description, and its orbit looks something like this. This is the orbit of the S2, and this is actually the for comparison, this is the solar system with the orbit of Sedna in red and orbit of Neptune and other planets right there as a tiny circle in the middle. So S2 actually orbits around the central black hole in approximately 15 or so years, and it basically covers a very large region of space in that period of time, and it moves really fast. When it gets to the periapsis right here, the closest approach, it moves at a speed of about 5,000 kilometers per second. And at this point, it's also experiencing a gravitational acceleration of about 1.5 meters per second square, which is about the sixth of the gravity of Earth. And at this point, it also actually loses a huge part of its heliosphere, the so-called area where you can actually potentially hold planets and other things in orbit around yourself. I'm going to show you what I mean by this in a few seconds, but let's actually just zoom out of here for a second and just jump to S2 right now, just to take a look at what we actually are observing and what we're seeing from its perspective. So I actually just wanted to show you, if we stay here and accelerate time a little bit, what all of this will look like. So you'll notice that as it moves around space, it's going to basically start orbiting this central region that's right there. It's in the back, and this is S2's orbit around Sagittarius A Star. Now, in Space Engine, it doesn't actually possess any planetary bodies. So if you open up its parameters, you'll see that there's really no planets present here. But I really wanted to discover if it's possible for this particular star to actually have a habitable planet. Now we're going to do a little bit of mathematics right now just to discover if hypothetically might have a planet with Earth-like conditions. In other words, we're going to take a look at the habitable zone, and we're going to take a look at the maximum distance of a planet, or the potential maximum distance for a planet around this particular star, whose mass, if you look right here, is about 15 masses of our Sun. So first of all, let's actually create a miniature Sagittarius A Star system with S2 orbiting around it. So there is the Sagittarius A Star, and I've tried to copy the actual orbital parameters from the 2002 paper that described the star in detail. And right around here, this is the point where the star is going to be moving at a speed of about 5,000 kilometers per second. Now it does actually show it here. There we go, 5,600 kilometers per second. And you will see that I've also added the habitable zone to it. And this is the area we're interested in determining whether it's possible to have an actual habitable world and basically habitable planet around it. Now, as you can see in this particular simulation, it actually does pass relatively close to Sagittarius A Star, and the distance between them is currently approximately 200-ish astronomical units. So basically, it is not super close, but it also is not super far. And then basically it does this every 15 years, and then it kind of leaves and moves to do its apoapsis for a pretty long period of time. But in this region, you could potentially have a habitable planet. Well, first of all, as you can see, Sagittarius A Star actually does pass through this region, so it would potentially disrupt any planet in this orbit. What I wanted to discover is, first of all, well, all objects have what's known as a heliosphere. It's the area or a volume, really, or a sphere around the object where it can potentially have a stable planet or stable asteroid belt or stable anything, really, stable orbit. So for this particular star, this is within its heliosphere and this is outside of it. So here it can potentially have a Mars orbiting around it, and here this Mars would fly away and start orbiting around Sagittarius A Star. We can actually calculate the heliosphere for this particular star by going to the heliosphere calculator I've used previously. And here, if we choose 15 masses of the Sun, which is the mass of this star, 4.3 million masses of the Sun for Sagittarius A Star, and the approximate value for the semi-major axis, which is about 980 astronomical units, you'll discover that the actual heliosphere is about 10.3 astronomical units. Now, that's average distance. At the closest approach, let's just say it's about 200 astronomical units, the heliosphere decreases to 2.1 astronomical units. In other words, if I go back to the simulation here, and maybe move S2 back to its original, not original, but closest approach, which is right around here somewhere. So right at this point, its heliosphere is much, much lower. It's only about 2 astronomical units. So you can only have a potential object orbiting in this region right here. And as you can see, because the star is already quite massive and quite big, it means that only planets really, really close to the star would be able to actually remain in orbit. So this already answers the question of the viability of having any kind of a habitable planet. And the answer is obviously no, simply because it can only survive here. And at this point, you can only really have things like hot Jupiters and hot Neptunes and so on. So this particular planet might actually stay in orbit, but even this seems to have escaped actually. Yeah, Sagittarius A Star kicked it out of the stable orbit. Now, for this star, the habitable zone is located in the region of space. That's, let me just show you in a second. That's going to be around, let's do this here. So from between 330 to about 640 astronomical units. So this is really, really far away, way beyond the heliosphere, way beyond the range where S2 can potentially maintain stable orbit of its planets. So what does this mean for S2? Well, forget about habitable planets. We're not going to discover anything here, and as a matter of fact, most of the stars orbiting Sagittarius A Star will probably not really have many planets left, because they'll all basically experience the same fate as Planet 9 right here. They'll get captured by Sagittarius A Star, because the heliosphere of all of these stars will decrease dramatically. And all of these planets and asteroids and all of the other bodies will start orbiting by themselves around Sagittarius A Star. So this will probably just end up having a bunch of like random stuff orbiting here all over the place. And a lot of this stuff, including like smaller rocks and so on, will just kind of start eventually moving closer and closer to the central black hole, and eventually may fall into it and get absorbed by it. And when this happens, we actually do observe unusual increase in all kinds of radiation coming from this region. This actually happened quite a lot, and most recently we've observed this, and not just observed, but actually captured this by New Star telescope, and you can kind of see it right here. So this was before the flare, and something fell into the black hole and the flare occurred, and this is the post-flare radiation coming off Sagittarius A Star. Now, there were some really big ones. As a matter of fact, we think that about 400 years ago, there was a tremendous flare that increased the radiation by about 1 million times. But these happen not very often, and usually they happen when some kind of an object actually falls inside the central black hole. But going back to S2, so it seems that it can only have planets that are orbiting really, really close to it, or not just planets, but any objects. And those objects would most likely be super, super, super hot, because at this distance, anything is going to be, I'll just place Jupiter here, anything is going to be at the temperature of like several thousand degrees Celsius, or really Kelvin. And in this case, this Jupiter will probably stay in this orbit, but get to temperatures of about 3,000 degrees. So no habitable worlds around Sagittarius A Star, most likely. And so let's actually see if this survives. Oh no, look at that. Jupiter also got captured by Sagittarius A Star. So every time it passes by close to it, the actual heliosphere decreases so much that it pretty much loses most of the planets. But anyway, so this suggests that there's very, very, very unlikely to be any habitable worlds around Sagittarius A Star, even around smaller stars, because a smaller star will actually have even smaller heliosphere. And so for any of these stars to have habitable planets, they would have to be relatively massive, and if they are massive, their radiation will basically increase the size of the habitable zone, and thus prevent it from having any habitable planets. So as you can see, for S2, the habitable zone is actually going through the Sagittarius A Star, which is not something that we wanted to see. So this particular video is going to be focusing on the discovery of a relationship between supermassive black holes in the middle and the creation of stars in the galaxy. Alright, well, let's backtrack a little bit, and let's actually talk a little bit more about the creation of stars and galaxies. So let's place Sagittarius A Star, the supermassive black hole of our own galaxy, in the middle, and then just kind of place a bunch of random stars around it to create a very interesting, but I guess somewhat not very realistic looking mini galaxy. So we're going to be creating this microcosm of a galaxy. So imagine this is the inner region of the galaxy, where a supermassive black hole is right at the center, and it has these stars, including some of the giant stars, orbiting around it. Now, once in a while, some of these stars will actually, as you can see right here, fall apart, and they will probably get sucked into, well, not sucked into, but get attracted to Sagittarius A Star, and get essentially, I guess you could call it swallowed, but it's not really swallowing. In other words, they're going to get destroyed by Sagittarius A Star, and this process will actually create a tremendous amount of energy. And this is actually when we call galaxies AGNs, or active galactic nuclei. Now, in some cases, some galaxies actually stayed active for quite a long time, but one thing that makes them very, very unusual and very special is that they actually start emitting a tremendous amount of energy that can also be visible really far away. And those galaxies in most cases are known as quasars. They actually become so bright that you can see them from essentially the edge of the universe. Let me see if I can maybe simulate some of those explosions here to try to release some energy from Sagittarius A Star. And here we go. So here's our miniature AGN. So it just swallowed some energy, and okay, I also apparently destroyed my black hole. That's not good. But basically think of this as energy being released, and oh wow, there's some cool stuff going on here. As it is being released, it starts to emit a lot of various radiation. So I guess this would actually be a pretty good simulation of what might happen here. Now, the interesting phenomenon here is that as this, and imagine this is actually the supermassive black hole in the middle. Now we're going to switch a little bit. Imagine this is actually the energy that's being released here from the center of the galaxy. This energy actually also influences the inner galactic core as well. So if I were to go back to the original simulation of the galaxy here, and look at the core again, this region right here is being affected by the emissions from the black hole. And these emissions will actually prevent new stars from forming, because they will, not only will they actually expel some of the gas from here, but they will actually heat up a lot of the space dust molecules. And these molecules will actually start gaining more kinetic energy and fly farther and farther away from the center, and thus will probably not even collapse into the stars. In other words, the more energy is expelled from the black hole in the middle, the more likely that the formation of stars in this galaxy will actually stop. And so this is the discovery we made in 2017, and the paper was actually published on January of 2018. It turns out that if you were to look at similar galaxies with similar number of stars in them, and then compare the actual size of the black hole in the middle, the galaxies whose black holes are not as massive, so let's just reduce mass here a little bit, the galaxies where the mass of the black hole is smaller will actually have star formation enabled for much longer, and will thus probably even have more stars at the ends. So there will be more new stars created, because the galactic core doesn't have a black hole massive enough to essentially destroy more stars and to produce more energy. Okay, let's try to visualize this again. So here we're going to take Sagittarius A Star, that's about 4 million masses of the Sun, and another black hole that's going to be almost 3 times, or I guess 2.5 times bigger, at 10 million masses of the Sun. Now, if you were to actually wait long enough, and that's of course assuming that both of these galaxies start with a relatively similar amount of stuff to begin with, you would realize that the galaxy with a slightly smaller black hole in the middle will have a lot more stars created. And these stars will also be somewhat younger as well, because the creation of these stars hasn't really been deactivated, or has actually lasted for much, much longer time. And as a result, there's going to be more overall stars here, whereas the more massive black hole, the one that's 10 million masses of the Sun, will have deactivated its star creation a lot earlier, and at the same time will have probably a lot less stars, or a lot of older stars and almost no young stars. So there's going to be a lot of neutron stars here, a lot of smaller black holes, but not as many actual main sequence stars. And this is actually a very interesting discovery, and also a very interesting relationship that we discovered, because now, by looking at a galaxy far, far away, and by sort of estimating the mass of the central black hole, by looking at the speeds of stars moving around it, we can then put it on a relationship graph where we can discover how many total stars it actually maybe has. And vice versa, by looking at the total number of stars, or estimating total number of stars, we can then maybe estimate the mass of the central massive black hole. So this relationship was not very well known to us until recently, until we looked at a lot of these galaxies far away and analyzed them in a lot of detail and basically discovered this very linear relationship between a mass of the central black hole, the number of stars, and the period when the star creation gets deactivated. So in our galaxy, the stars are still being created, but not so much in the central region. But our black hole is not as massive as some of the other ones. But there are galaxies out there where the star creation has already been deactivated because the mass of the central black hole has created so much energy around it that a lot of the gas has been expelled, and so the star creation is no longer available to it. So all in all, it's a very interesting discovery. It maybe not as practical as some of the other ones, but this relationship allows us to understand other galaxies a lot better now, and we can now even maybe use this to create a very detailed list of various supermassive black holes out there by looking at those galaxies and also the number of stars around them. Anyway, so that's all I wanted to discuss in this video, and this is video number 2 about 2017 and early 2018 discoveries about black holes. And in the next video, we're going to talk about one more discovery we made very recently about these unusual, beautiful objects. But for now, let's actually watch what happens if we run the simulation a little bit longer, because I have a feeling that these two tiny miniature galaxies are actually going to collide with each other and possibly create some really cool effects. Although I did place them in orbit around one another, so maybe they never will. Maybe they'll actually end up spinning around each other forever. Oh, look at that. Here we go. That was actually pretty interesting. We got a miniature interaction between them, and it seems like the smaller Sagittarius A Star has lost a lot of its stars, while the bigger galaxy possibly even stole some of the stars from Sagittarius A. And this is maybe something that we'll experience one day when the Andromeda galaxy, that's much more massive than the Milky Way, comes close to our galaxy and actually collides with it. And so what I actually wanted to do in this video is mention some of the history behind black holes and also just explain the information paradox and kind of give you an idea of what we think will actually happen to black holes once they evaporate. So first of all, what exactly is information paradox? Well, in a nutshell, it talks about the idea of everything falling into a black hole that, has information. Like, for example, the information about how many atoms are in your body and what kind of atoms they are and how they're structured. All of this is information, and when it falls into a black hole, it technically may disappear. Now, in 1975, Stephen Hawking, the most famous black hole scientist, studied the behavior of the so-called quantum matter in the vicinity of black hole and basically showed that, well, first of all, there's no way back from a black hole. Second of all, they're not really black, they actually emit thermal radiation, just like hot objects. But he also speculated that it's very likely that information is lost once it enters a black hole. And his reasoning behind this was that, well, a radiation from the surface of a black hole is very limited. It actually is formed by these particles and antiparticles that are kind of split into two. And I've talked about this concept previously if you want to check out one of the previous videos. But the idea is that it's only determined by a few parameters. It's not enough to represent the entire information. But in the late 90s, other developments in physics, specifically the string theory, convinced the researchers that information that falls into a black hole must come out when the black hole evaporates. Now, how this happens is still very unclear. And one of the reasons why it's called information paradox is that, well, we believe time and space are connected and they can basically go either way, frontwards or backwards. In other words, you could go back in time. Now imagine if you fall into a black hole, if your information disappears, if you were to rewind time, how would information form out of nothing? So in other words, if you were to literally rewind time, nothing can just create something out of a black hole. So this information has to be stored somewhere. And that's essentially the idea behind this information paradox. The information that goes inside black hole must be stored somewhere in the black hole. Now, as of 2017, we're actually still not entirely sure what exactly is happening on the surface of a black hole, but what most scientists argue today is that when it comes to at least electromagnetic energy, for example photons, since there's actually infinite number of new charged particles on the surface of a black hole, there are probably infinite number of quantum soft hairs that a black hole can support. Now, what is a soft hair? Well, in a nutshell, it's basically a low energy quantum excitation. It's an excitation in the actual quanta itself that releases information when the black hole evaporates. Well, maybe the picture will do a slightly better job. Now think of it as an energy excitation on the surface of a black hole on the microscopic levels. So analysis must be repeated for the gravity, of course, because that only talks about photons. So we don't really know if this is actually something that applies to everything. But nevertheless, the soft hair they introduce is probably something that we need to study a little bit more, but also it's unfortunately not enough to capture all of the information about what falls into a black hole. So once again, if you fall into a black hole, this soft hair theory is not enough to explain what happens to your information. Over time, as the black holes collect this information, today some scientists speculate that all of this information is somehow stored on the surface, and basically the three-dimensional information is turned into two-dimensional information, and in a sense, it becomes kind of like a hologram on the surface of a black hole. Now, what happens to all of this afterwards? Now that's of course another question. Are black holes actually tiny time bombs that will eventually result in this huge explosion of all of this information, possibly even create completely new universes from all of this information that's stored in them? Well, that's of course something that we won't know until the future, until one of the black holes actually reaches the end of its days. And since the evaporation of a black hole is a very slow process, the so-called Hawking radiation takes like billions of years to evaporate even the smallest black hole into non-existence. We won't really see any of this happening anytime soon. But, theoretically at least, when a black hole evaporates, it can no longer hold this information. So what's going to happen to it afterwards? So will all of this information just be left as a kind of a crystal, basically an unusual component that just stays there after the black hole evaporates, or will it actually suddenly explode, creating a completely new universe and possibly result in a new Big Bang? Essentially, will a black hole eventually create a new universe? And if this new universe is created, is this how our universe started? Now, some scientists still think that black holes store information in some kind of a, basically like a tiny pixel, a quantum particle that is really small on the surface of this black hole. But if a black hole becomes smaller and smaller, what happens to these tiny pixels? And although maybe some of the information is actually carried away by the Hawking radiation as the black hole evaporates, will this actually release all of the information, or will some of it still be stored inside and thus generate some kind of a information bubble at the end when the black hole is gone? So all of this is actually very interesting, but possibly might give us an idea of how universe actually behaves, how it's born, and how it dies. And for all we know, maybe a long time ago, our universe was also a black hole that basically exploded. So we've actually been looking for these types of black holes for quite a long time now, and we were able to discover what's known as an intermediate mass black hole in August of 2017. These were actually very hypothetical at first. We didn't really know if they were real, but we finally were able to see one, and we were finally able to get so much closer to understanding of how our galaxy is created, and essentially how these massive black holes create supermassive black holes. So anyway, we're going to be going to the center of our galaxies here just to see what's there on the inside. Very, very close to the supermassive black hole known as Sagittarius A Star, which is the black hole at the center of our galaxy. The scientists from University of Keio in Japan, specifically here, I believe it's a person by the name of Dr. Tomoharu Oka, basically was looking at the various types of molecular gas that is present very close to this region, and using various simulations they were able to establish what would actually happen if a black hole was inside of this gas. And it just so happens that they were able to see very similar effects in real life to what they simulated. And using these simulations, the team believes they discovered what's known as CO0.40.22, another name for a very unusual intermediate mass black hole. And let's actually use Universe Sandbox 2 and try to discover exactly what was found and what it means to science and to our understanding of the universe. So here's our galaxy, the Milky Way. There is Sagittarius A Star in the middle there. Our sun is somewhere over here. And basically we're looking at the molecular clouds very, very, very close to this region right here, almost within this region. Now we're going to actually slow down time here just so that the galaxy doesn't fall apart, and just so that we can actually see things in a little bit more human terms. And so what we're going to do is we're going to choose a black hole and place the black hole that's about 100,000 masses of the sun. And so right there, right in the middle of the Milky Way, very close to Sagittarius A Star, is this black hole known as CO-040. Or I believe there's a point in there missing somewhere. Yeah, this should be 0.40 and then -0.22 star. Star refers to the fact that this is a black hole. And if we were to zoom in, this is actually what it would look like. It's about 100,000 masses of the sun, so it's only about 2% of the mass of the supermassive black hole Sagittarius A Star, so it's significantly smaller. We can even compare them in size by basically placing them next to each other. And it's essentially there, just kind of flying through space, disturbing gas, and creating no other fuss. And the reason we were able to discover it is because of this fuss that it creates inside the molecular cloud. Now here we can actually accelerate time a little bit now just to see how things spin. And basically, the interesting thing about this black hole is that, well, it's inactive, so it doesn't really have any accretion disk, it doesn't have any jets coming out of it, and it would be very, very challenging to see otherwise. And the reason why it's important that we've discovered this is because we were actually predicting these black holes for quite some time now. We actually thought that these exist in the center of the galaxy, and a lot of them orbit around the central supermassive black hole, but we were never able to see them. We were actually never able to detect them because it's very, very difficult to find them. They're practically invisible. They don't emit any light. They don't really cause any disturbance otherwise. And just because this one was inside the molecular cloud, we were able to see it slightly easier. Now, let's just actually compare its size to our own sun, for example, just so you can get an idea of how small this thing actually is. So our sun is right there, and this is essentially smaller than our sun. It's maybe closer in size to actually Jupiter. So Jupiter would be just a little bit smaller than this black hole in terms of the actual size. Okay, why is it important that we found it? Well, these black holes are sort of hypothesized to create the supermassive black holes at the center of the galaxy. So we think that this is actually the progenitor, or basically the part of creation of these larger black holes. And so one day this one might actually collide with this one and make Sagittarius A Star even bigger. We're still kind of not sure how these supermassive black holes, such as Sagittarius A Star, are created, but we think now, because we found this other one smaller next to it, we believe that maybe this is how the supermassive black holes are created. In other words, let me just run a simulation for you just so you can actually see. Okay, so here we go. We're going to try to simulate this in very, very brief terms. So here is a progenitor supermassive black hole at the center of the galaxy. It has a bit of a accretion disk going on, and it has other black holes orbiting around it. And there's probably other stars here. We can actually just add a few stars for fun as well. Let's just take a few, like, maybe just actually randomly generated main sequence stars. And we're going to just place all of this together just so you can kind of see how all of this is going to interact together. And then there's going to be a few intermediate black holes in between that are going to be falling inside of this black hole. So I'm actually going to decelerate time just so that you see how all of this starts interacting in real time, or maybe almost real time. So the accretion ring is orbiting, everything seems to be working. Let's accelerate time and see what happens. So you'll notice that the intermediate black holes will slowly start approaching the black hole in the middle, and they'll actually start disturbing the accretion disk. Obviously, they'll start disturbing the stars orbiting around this black hole, but most importantly, they're eventually going to get absorbed by this black hole. And as they get absorbed, as basically it acquires more and more mass, it is going to grow in size and create larger and larger event horizon around it, or as it's more recently become known, the apparent horizon. So let's just run the simulation for a little bit, and it looks like it's actually going to be really slow because of the accretion disk, but we might have no other way of doing this, so we're going to disable trails and just wait. And so here comes the first black hole that's about to get absorbed. It's falling right into the supermassive black hole, and there you go. And as the black hole in the middle acquires more and more mass, it's going to start attracting more and more things. And so essentially this is what we think may have happened in the beginning of our galaxy, when the black hole in the middle ate all of the other black holes nearby and grew larger and larger and larger. It might be actually easier to see if I remove the dust particles that are orbiting around this. So I might have to actually just go ahead and delete all of the particles because it's a little bit easier to see. But there you go. You can kind of see things will start falling into the black hole slowly, and it's going to start growing larger in size. So if I were to enable mass here, you would see that with time it starts acquiring more mass. And this is what we think may have happened. We were theorizing about this for many years, but couldn't really prove it until we discovered the intermediate black hole in August of 2017. And now we think we understand the creation of the galaxy a little bit better, and it seems to be making a little bit more sense to us. And so essentially that's why this finding was kind of important. This is why I wanted to talk about it in this video. And hopefully in the future findings, or I guess if we keep doing more research around this region of space, we might discover more of these intermediate black holes, and thus proving this hypothesis and basically making it a theory of creation of the galaxy and creation of the supermassive black holes in the middle. Hello wonderful person, this is Anton, and in today's video I wanted to play around with Universe Sandbox and try to recreate this kind of an unusual new view of a black hole from Stephen Hawking, using not event horizon but apparent horizon. Let's play around with the game and see if we can create something that might be visually appealing. Anyway, welcome to What the Math. So in one of the previous videos, I talked about how Stephen Hawking now thinks that event horizons, basically these things, that you can kind of see on the outskirts, basically the part of the black hole that we kind of usually call the black hole. So this part right here doesn't exist. He doesn't think they are real anymore. He now thinks that there's something called apparent horizon, where a lot of the information basically kind of gets trapped and stored and then released through, such as, for example, Hawking radiation, or maybe even other means, in a completely different manner. So he basically thinks that the information paradox can be resolved by introducing this kind of apparent horizon into the black hole equation. And so we're going to try to maybe mimic this. So we're going to ignore the fact that this black hole has actually, let's just do this from scratch. We're going to ignore the fact that this black hole has anything. We're going to assume that it's basically just a tiny minuscule supermass. So we're going to choose something maybe 100 masses of the sun. I actually before tried to change the size just to make it super minuscule, but it didn't work. I don't think the game allows me to change the size of a black hole, unfortunately. So we're going to have to stick with this for now. Now let's place a few things in orbit around it, just so that we can create something that looks a little bit realistic. And so we're actually also going to rename this into Stephen Hawking's black hole, because it's basically his new view of how black holes probably look. Now we're going to start adding things to it, and specifically here I want to just add a few rings. And let's start by maybe introducing a few objects that will create a few collisions and very likely cause a bit of a disturbance here. So we're going to just introduce some bodies into this black hole, and this will probably cause a bit of a destruction. Here we go. So there's our bodies. They actually, for some reason, flew away right away. Not exactly what I expected. And we're also going to maybe introduce a few rings here as well. So I actually do want to have a few rings around this black hole. And I think I may have introduced a little bit too much stuff. There's just a tremendous amount of things going on here right now. So we're going to remove some of this just a little bit, especially because the moons that I introduced seem to be causing a lot of destruction. But this is actually what black hole environment might be even like, because it's very destructive. There's a lot of things going on here. And for the most part, there's a tremendous amount of energy that's being generated through constant destruction. Now, right in the middle, we're actually going to create something very special. We're going to try to create the apparent horizon. Once all of this settles and once all of these objects disappear, we might actually have to remove some of them, especially the fragments, because we don't really need them, at least not as many as I've created here. And so let's remove the fragments as well. And so now you may kind of see that there's something going on around the black hole. There's this unusual, almost like a halo around it. Basically a ghost-like appearance. And this is one of the first things I wanted to create. I wanted to create this kind of a dust-like cloud around my black hole, just to kind of give you an idea of what apparent horizon might be like. But this is not it. I wanted to create something else. I'm actually going to create a simulation of what it might look like as this information and as all of this matter falls into the black hole, what it actually might appear like to us from an outside, for an outside observer. So the way we're going to do this is by basically adding several spherical rings with maybe a slightly different color, just to make it a little bit more interesting. And these rings will actually be very close to this black hole. And it's only going to be on the surface of this black hole as well, so it's going to be even more unusual in that sense. And so let's hope this works. We're going to add them right around here somewhere. I don't really see where they are. Alright, so here we are. Here's actually the first spherical creation that I wanted to make here. And we're going to actually add a few. We're going to just make it like a lot. So this is what this kind of a chaotic information might be represented as on the surface of a black hole. Now, it's suddenly super slow, and don't forget that this is actually not in real time. This is like 1,000th of a second per second. And so what you can kind of see here is what I think Stephen Hawking actually imagined in his paper that he wrote in 2014. This a very unusual apparent horizon, this information that's essentially stuck on the surface of the black hole, where we think event horizon maybe is, but he doesn't believe in event horizon anymore. And some of this information once in a while escapes as Hawking radiation, or maybe through some other means, and you can kind of see that not all of these particles are stuck to the black hole. Some of them actually do escape. Now, this is not the best representation of the apparent horizon, but this is the best I could do using Universe Sandbox. And obviously around the black hole there's also going to be the accretion disk, which we're going to create using a very different sort of color. And so now in super slow motion you can kind of see what black holes might be like according to Stephen Hawking. So there is that apparent horizon with its information. There's obviously nothing on the inside, there is singularity in the middle, and if you move out of this apparent horizon, around it you'll have the accretion disk, which is here in yellow, with a lot of other stuff flying around it, and obviously stars in orbit as well. Some, or I guess most black holes have stars around them. And well, so here you go. Here's your slightly more accurate representation of a modern view of a black hole according to Stephen Hawking. Now, maybe this is not exactly how he imagined it. Maybe it's not purple in the middle, doesn't have these yellow blots, but this kind of gives you an idea of the apparent horizon that he envisioned, and also obviously the accretion disk that we know is there. And this is just so we can actually explain the so-called information paradox, about which Einstein talked about a long time ago, and about which Stephen Hawking talked about something like 40 years ago, and we still have no resolution about it. So basically that's the paradox of information not really disappearing when it enters black holes. Something must happen to it. Anyway, so that's all I wanted to show you in this video, and I wanted to create and kind of help you visualize the modern representation of a supermassive black hole, or really any black hole for that matter. But in this case, it's a black hole that's about 100 masses of the sun. So this is actually going to be a three-part video where I wanted to start by examining three relatively interesting and unusual things we discovered about black holes. In this part one, we're going to be talking about the strange, unusual filament that we saw emanating from the central black hole in the middle of our galaxy. Now, I didn't actually create a very realistic black hole here. This one doesn't really have the accretion disk. It doesn't have the relativistic jets coming out because they're not really that important for this video. I wanted to just have an actual black hole with the mass of 4.3 million suns, very similar to the one in the center of our own galaxy. Now, what exactly did we discover? Well, first of all, here is actually the picture. You kind of might be able to see the little string coming out of there. And this is actually what the scientists saw, and they have no idea what this is. And so I've decided to kind of try to recreate this particular unusual phenomenon, and just to kind of demonstrate this in Universe Sandbox, just to see if we can maybe, just maybe, make it look relatively similar. So it's essentially a very unusual string that seems to pass through the black hole, or possibly relatively close to the black hole, and it doesn't seem to have a very good explanation just yet. Well, so there's three suggestions as to what this might be. Well, first of all, we can see that it's kind of thin, and it's also not particularly straight, so it does bend a little bit. And for this reason, one of the suggestions is that this is some sort of a very long string of magnetized particles that are basically being bent and shifted and displaced by the super powerful magnetic field around the Sagittarius A. If this is correct, then this also suggests that maybe, just maybe, we can actually use this particular string that or this filament that we detected, to study the super strong effects of the magnetic field around Sagittarius A, and also possibly even be able to predict some of the other phenomena, because being able to see the magnetic field here would be very, very, very important. Now that's the first sort of suggestion. As you can see, my particles already started to fall into the black hole because it's a little bit too strong for them to resist. The second suggestion is not as fun. The second suggestion basically says that maybe, just maybe, it's just some sort of a statistical anomaly, that it really is just something that occurred for the time being, and that many such filaments exist out there in the universe. We just haven't really seen them before, but this one just happens to be close to our black hole. Not as fun, but also a possible explanation. But the third one is really the one I like the most. The third explanation suggests that this very long filament is what might be known as a cosmic string. Now, not exactly the so-called string theory string. This would really refer to something that is essentially an extremely long, extremely thin structure that exists throughout space and was actually created during or just after the Big Bang. These strings would be about like 1 proton in thickness, but super dense, and would be able to produce a huge amount of gravity. As a matter of fact, 1 kilometer long string would produce more gravitational attraction than our own Earth. And if they're bent like this, they will produce even more gravitational field. Now, these particular very unusual theoretical objects have never been detected. They've been speculated about. They've actually been relatively thoroughly theoretically explained using various mathematical models, but for the most part, we don't really know if they're real and if this is one either. I guess only time will tell, because we'll need to study this particular object in a little bit more detail. But we know that these cosmic strings would actually be able to carry not just mass, but also electric current. And the hypothesis is that usually they will kind of migrate toward the center of the galaxy where the black hole would be. And in this particular case, maybe, just maybe, one of those strings got captured by the event horizon of Sagittarius A. And so now it sort of stretches all the way from Sagittarius A to the rest of the galaxy, which actually makes it kind of interesting and kind of cool. So in other words, this kind of would maybe suggest that out there in our universe, there's lots of these very unusual, super long, super thin objects with a lot of gravitational abilities that are actually, or could be potentially used for various means, including, of course, interstellar travel, because you could probably find a way to propel yourself along the string. And also, they would probably help us explain a lot of other phenomena, including maybe things like dark matter. But for now, that's all we know. And since we've only recently discovered this in 2017, it will probably take a while before we can fully explain this particular object. Hello, wonderful person. This is Anton, and in today's video, we're going to be going on a little trip. Well, okay, not so little. We're going to go on a long trip and try to find the largest galaxy in our universe, and then try to find the black hole in the middle of it. Let's go and explore IC 1101, and welcome to What the Math. So how far away are we going exactly? Well, the distance is actually going to be about 1 billion light years. That's, when you think about it, is pretty far. I'm going to show you where we're going just right here from Earth, just so you can kind of imagine how far away it really is. We're going to go into the search here and type IC 1101. This galaxy is actually relatively well known to us, and we've discovered it quite a long time ago. Specifically, actually back in 1790 by the British astronomer William Herschel. As you can see, from this distance you can not really see it very well. When we originally discovered it, and then for about 200 more years, we actually thought that this was basically a nebula. So, in other words, this was, according to early scientists, early astronomers, essentially, okay, there it is. You can kind of see it now. This was most likely a formation based on a star exploding or a planet releasing a lot of material. Back then, people didn't really understand these very well. Until Edwin Hubble, back in 1932, realized that these were actually galaxies. They were completely separate entities far, far, far away. Well, anyway, so today we're going to go there. We're going to jump to this location, but first let's actually exit our own galaxy. And we only have one goal. Our goal is to discover the black hole, the central supermassive black hole in the middle of this galaxy. Now, if you know anything about our own Milky Way, our black hole is about 4.3 million masses of our sun, and our galaxy contains approximately 100 to maybe 300 billion stars. Hopefully you know what these numbers mean, so that I don't have to write them down for you. The galaxy we're going to has approximately 100 trillion stars, and on top of that, let's actually make this a little bit brighter. On top of all of this, the galaxy we're going to has a black hole that is most likely about at least 1,000, but possibly several thousand times more massive than our own Milky Way galaxy. And the current estimates for this particular black hole are somewhere in between 40 to maybe 100 billion masses of the sun. So it's going to be a long trip actually, but we're going to make this relatively short by accelerating a little bit more and flying through space. All these little spots you see, these are other galaxies. And we're going to this really large one that you're going to see in a few seconds. So the thing about this particular galaxy is that even though we've known about it for a long time, we still kind of haven't really discovered any other interesting objects inside. So we know that it has a large black hole, we know that it has a lot of really ancient stars, specifically a lot of metal-rich stars that are anywhere from 10 to possibly even 12 billion years old and are still kind of around and are kicking. In other words, a lot of the stars here are much older than the stars in our own galaxy. And there it is, it's coming up in your view right now. And one thing we don't really know about this galaxy is how exactly it formed, how it got to be so big, and also what its actual size is. So it's kind of difficult to measure these large galaxies, specifically the type of this galaxy being elliptical. It's kind of hard to estimate the actual dimensions and the actual borders here. But estimates vary quite dramatically actually, and most people today at least kind of think that this is about 200,000 to maybe about a million light years in radius, and specifically here you can see that the diameter is actually 6 million light years, so making this 3 million in radius. And these estimates do vary depending on the study, but the idea is very simple. This galaxy is kind of really spread out, unlike other galaxies. And even though most of the brightest stars and brightest features are actually within about 200,000 light years, the other part extends up to about 3 million light years. And that makes it at least 10, but possibly even 20 times bigger than our own Milky Way. So we're going to jump inside of this, and as you can see, it's very sort of elliptical and amorphous. It doesn't really have any features here, and there seems to be also a dwarf galaxy orbiting around it right there, irregular dwarf galaxy. And we're basically going to go inside and try to find this supermassive black hole on the inside. It might be challenging because we're basically moving through 100 trillion objects, but we're gonna do our best. And you also get to see what it actually feels like to enter such an unusual galaxy in real life as well. So this is as if you were jumping into the galaxy in some sort of a super fast spacecraft that moves at several thousand light years per second. Alright, so we're going to be following this arrow that you saw on the screen. It's actually guiding us toward the supermassive black hole. And around several thousand light years, we're going to slow down and start moving a little bit slower until we get to several light years away from it. Alright, so we're about 13,000 light years away. If you know how far away our own Sagittarius A is from Earth, it's about 27,000 light years. So here we're basically already in the central region of this galaxy. Now, everything is super white right now. Everything is ridiculously bright. And that's because there's so many stars and so much dust here. I'm going to reduce the illumination a little bit. And you can actually kind of still see other stars and other galaxies through all of this dust, but it's not really that easy. But yeah, anyway, so, oh, I missed it. It's actually, I think it's in this globular cluster right there. There you go. I think this is where we're going right now. So in the middle of this cluster, it's very likely that there is a ridiculously large black hole. So let's go and find it. So we are right now literally in the center of the largest galaxy in the universe, at least the largest we've found so far. And oh my god, look at that. We got really lucky. I actually just bumped into it completely by accident. Well, looks like that's it. This is the supermassive black hole in the middle of IC 1101. So we're going to actually accelerate time a little bit because I want to see if there's any other objects orbiting around it. I'm going to try to discover if there are any other stars here. And I'm not pointing the right object. I have to point right in the middle of this. And so let's actually see what mass it has here, because this is significantly larger than our own Sagittarius A Star. So let's move around it. And I think that's it. Yeah, there we go. So, okay, this is at a distance of 0.3 light years away. And this is actually pretty far when you really think about it. And the diameter of this black hole is 412 astronomical units. That's at least 10 to 12 times bigger than the Sagittarius A Star black hole. And the current mass is showing at, I think it's 10 billion masses of the Sun. So maybe a little bit on the more conservative side, because we think it might be even 100 billion. But yeah, this is a ridiculously massive and ridiculously large black hole. Now, if I click on the button right here, it will tell me what stars it has around it. And here, we actually, surprisingly, have quite a lot. So it seems that most of these stars are actually kind of a similar type. These are all M-type stars. In other words, I think for the most part, they're all red dwarfs. And that kind of also explains why this galaxy is such an unusual yellowish color, because a lot of these stars are really old. They're all basically ancient stars that remained or stayed around after the early life of this particular galaxy, when a lot of these stars and a lot of these different objects were more blue in color and more white in color as well. Alright, so we're going to change the lighting here. Possibly maybe decrease it a little bit just so it's easier to see. And there you can kind of see one of the stars orbiting around this black hole. Let's actually maybe zoom out just a little bit so you can see other stars here as well, just to kind of appreciate the size of this monster. There you go. You can see the little stars orbiting around a supermassive black hole. Now, I think it kind of is difficult to really see how large this object is. So just to help you visualize, I'm going to move really close to it and help you understand how ridiculously tremendous this object is. So let's actually select it again. We're going to go here, and we're going to move a little bit closer and basically just take a look at practically the event horizon, or the surface of this black hole. So at this distance, right around here, okay, no, maybe around here, which is 1,000 astronomical units away. Actually, maybe a little bit closer. Here we go, 700 astronomical units. So right here, we're practically almost at the event horizon. And this is a distance of basically Sedna at its farthest point to the Sun. Sedna is one of the farthest objects we found in our solar system. If I move a little bit closer, so basically if I move just a little bit closer to this object, right before we enter the actual event horizon, we're still actually at it, so right around here. We're about 15 times more far away than Pluto is from the Sun. So if the center of this black hole was the Sun, we're currently at a distance of 450 astronomical units, which is basically about 15 times as far away. So this is how ridiculously large this object is. And interestingly, This is actually not the largest black hole out there. There are ones that are even more massive and obviously bigger as well. And well, so there it is. This is the supermassive black hole in the middle of the biggest galaxy we've ever discovered. And we're going to just kind of get inside of it for a second to see what it would look like right from the edge. So there you go. There is that view, one-dimensional view of being inside of the black hole. And basically, as you move closer inside, it kind of closes behind you and disappears forever. But we're not going to do this. We're actually going to escape away from this black hole and just take a look at it once again from the outside, using default settings for light and for magnitude as well. So this is kind of what the center of this galaxy looks like, and it's very, very different from what you observe in the Milky Way. There's a lot more dust, there's a lot more really ancient stars, and there's definitely a lot more interesting and very unusual events that we don't really know of yet. There's probably things here that we've never seen in our own galaxy, and there might be actually things here that we might be able to discover one day if we have a powerful enough telescope. Hello wonderful person, this is Anton, and in today's video we're going to be going to the middle or the center of our galaxy and talk about a recent study that basically suggested that we finally discovered various types of black holes very, very close to the actual center of the galaxy. Anyway, welcome to What the Math. So this new study actually is based on the theory that suggests that right next to the central black hole, basically Sagittarius A Star that we're going to be visiting in a few seconds, within about 6 to maybe 10 light years, there should be a tremendous amount of black holes, specifically close to about 10,000. So let's actually first go to the Sagittarius A Star, which is right there in the center of this very large globular cluster. And here, if I go to a distance of about 6 light years, or let's just go to a distance of about 10 light years, which is approximately this far away, within this distance there should be a tremendous amount of black holes. Now, for the longest time we couldn't really find any. As a matter of fact, as of today, there's only about maybe 60 or so black holes we've discovered in the entire galaxy. And that's not really even close to the theory. And this so-called density cusp, as it's known, has been basically nothing but a theory. Now, in Space Engine, if I were to come closer to the central black hole and to then search for any kind of black holes within 20 light years away from us, or even more than 20, I can actually even put 50 light years, I will unfortunately find nothing. So even this game, okay, there's one here at a distance of about 50 light years, but even this game is currently set to basically only detect black holes with a much lower frequency. But the reality is that most scientists or most astrophysicists today believe that there are a tremendous variety of black holes within about 1 parsec away from Sagittarius A Star. In other words, within about 4 light years of the central black hole, which is right there, there should be close to about 20,000 of these beautiful objects. Now, where exactly are they? Well, it turns out, and this is coming from a very recent paper by Charles Haley, Kaya Mori, and Franz Bauer, and a few other people. This was actually posted in Nature magazine very recently in April of 2018. Turns out that they actually used previous data from the Chandra telescope, and what they did was look at the binary, specifically the so-called X-ray binaries, similar to the Cygnus binaries. Basically, these are binaries containing a black hole and another object. And normally these can be relatively energetic, but they were looking at just regular binaries that may actually have black holes that have these things. They would have an accretion disk. And these accretion disks in binaries will actually produce a little bit of X-rays. Not a lot of X-rays, but a little bit of them. And so they actually just looked at these more or less not so energetic black hole binaries. And what they discovered was basically at least a dozen of these objects within about 1 parsec of the central black hole. They actually even took a photo of it, which you can see on the screen right now. And so this is the Sagittarius A Star right here, and you can see every red spot that you see on the screen is basically an X-ray coming from most likely a black hole binary. In other words, they were able to discover quite a lot of these unusual binaries in this region that we haven't really seen before. And using statistics, we can actually estimate that there's probably a lot more singular black holes out there. So even though they only discovered about a dozen or so binary black holes, just based on the understanding of how black holes form and how binary systems work, we think that there's probably something like 10, possibly 20,000 singular black holes hiding out there very close to Sagittarius A Star. Now, this is within a distance of about 4 or so light years, so that's actually not very close, and I wanted to show it to you in Universe Sandbox just so you can get an idea of how far away it actually is in terms of distances. And so with Sagittarius A Star right here in the middle, we can place maybe a few smaller black holes at a distance where you would basically find these objects. So here we're actually talking about several light years, and that's actually pretty far away. So there's probably this many black holes they've discovered now, and these were all binary black holes, but at a relatively large distance. And as you can see, it's actually somewhat similar to the distance between our sun and the closest star to us, which is Proxima b, or Proxima Centauri, that is. Proxima b is the planet around that star. So it's not that close, but like I said, within this distance they expect at least 20,000 black holes, which is actually quite a lot. So it would look more, and I don't even know if I can actually try to put that many here, but it would look more like something maybe like this. Now let's see if it actually works. Okay, here we go. This is only 1,000 of them. So as you can see, the game has suddenly slowed down dramatically, and I may not even be able to run it very fast. But basically everything here is essentially a black hole, and all of these individual objects are sort of a representation of 1/20th of what we think is happening here, and this is within about 1 parsec. And so even though there are actually also stars here, there is actually a tremendous amount of these black holes, and this is what we refer to as the density cusp, mostly because we believe that a lot of these black holes came here from the outer edges of the inner galaxy, and they actually ended up closer and closer to Sagittarius A Star, and a lot of them actually do end up falling into Sagittarius A Star, thus increasing its mass. At least that's the theory behind it. Unfortunately, I can't really place any more. This is 1,000, I think, at this point. This is as far as my computer will be able to handle. And if your computer is more powerful, you can place all 20,000 just to see what it looks like. But basically, that's kind of what this region looks like. But because these are black holes, we don't really see them. As a matter of fact, we see absolutely nothing here, because they don't really emit any light. And if they're not in a binary system, they don't even have any accretion disk to basically provide any other energy either. They would only emit light if and only if something actually falls into them. Well, that's all I wanted to show you in this video, and now we know that the unusual region around Sagittarius A Star actually possesses quite a lot of invisible black holes that we don't really see. In other words, even though this was a theory up until now, we have now been able to detect at least a dozen unusual binary systems, which are quite rare usually, where there is, or at least might be, some sort of a black hole that is emitting X-ray radiation. There's really no better explanation for what it would be. So, what exactly are we going to be doing? We're going to modify Tesla Roadster's mass and its density and its size and turn it into something that will basically first eat up the solar system, and then we're going to go ahead and possibly even do a little bit more and maybe turn it into some sort of a supermassive black hole. Let's start by basically seeing what happens if you start increasing the mass of this object. And as you can probably imagine, with the increase in mass, the size of the object increases as well. Now, I want to start basically doing this until it just starts causing tremendous havoc on our solar system. This is obviously not the most scientific concept I could explore, but the reason I'm doing this is because I really wanted to show you that you can essentially turn pretty much anything into a black hole. A black hole is actually not something that is dependent on the mass as much as it is on the density. Now, to create a stable black hole, though, you do need to have a lot of mass. Alright, so we're in kilograms now. Let's actually just go ahead and give it like 1 mass of the moon right away, and boom, look at that. It's a Tesla Roadster that's approximately 7,500 kilometers in radius. It can have its own Tesla Roadster orbiting around it. And why wouldn't it? Why wouldn't it? Because of course it would. So look at that. It's a Tesla Roadster system? Planetary system? I don't even know. It's a system of cars where 2 cars are orbiting around one another. Anyway, moving on with our mass addition, let's keep increasing this. Now, the density here is actually still pretty low. I may actually start decreasing this. Although it doesn't seem to... Oops, wrong way. It doesn't seem to be affecting the car that much just yet, but I want to actually make this mass much higher first before we start doing anything else to it. So right now, this car is actually bigger in radius than our planet Earth. If I were to compare this to our beautiful planet, you would see that it's just a little bit bigger. But mass-wise, it's not. Mass-wise, it's actually significantly smaller, like 80 times smaller. So, technically speaking, we could actually crash this into Earth, and it would probably cause us a lot of damage, but it wouldn't really be anything that impressive just yet. This is going to be a topic for another video. Right now, we're just going to increase its mass until it becomes an Earth-like object. Bigger than Earth. Mass of Earth. Alright, so let's start increasing its density to the point where I actually want it to be density of water. So this right now is basically an ice-like object, 1 gram per centimeter cube. To make this into more of a Earth-like object, we have to change this into 5.5. So this would be an Earth-like object, size of Earth, mass of Earth, and pretty much density of Earth as well. And now we can start making this even more dense. So as a matter of fact, now that I have almost reached the mass of Earth, here we go, we're going to now change this into essentially a black hole-like object by reducing its size and increasing its density to the point where it's practically almost the same size as it used to be, but it's going to be tremendously dense. And this will actually be something that will indicate to us that it's slowly becoming more and more like a black hole. So here I have to increase my density to the point where it is basically around the same size as it used to be. Now here I have to be careful because I don't want the escape velocity to become speed of light, because that's when it becomes a essentially a black hole. The original car was what, like maybe 3 meters in radius, maybe 4. I'm not entirely sure actually. But even at this density, which is already a very, very high number, and at the mass of Earth, and only about 4 meters in radius, it's still not exactly a black hole just yet. So we actually have to change the escape velocity by a factor of about 20, I think. It has to become 20 times higher before it reaches the point where it is a black hole. Now I'm going to start increasing my mass again. And we're going to give it, let's just say 10 masses of Earth. Okay, well, maybe a little bit more. Let's actually make it very, very similar to Jupiter in mass. And at this point, its radius is about 27 meters. It is mass of Jupiter, so it's actually going to start attracting our planet Earth very, very soon, wherever that planet is right now. Oh, it already is. Look at that. And the moon is very fastly moving toward us, and so is the Earth actually. So we expect a collision from our moon relatively soon. But this is not the end yet. We're going to keep going and going and going until basically we reach mass that's even higher than this. Let's go for like practically 1% the mass of Sun. So at this point, even though our escape velocity is already very, very close to the escape velocity of a black hole, our mass and our radius... Oh, looks like something just collided with me. Anyway, so I accidentally pressed the wrong button, but I'm going to go back to 10 meters Tesla Roadster, and it is currently at the mass of 1% of the mass of the Sun. It has now reached the escape velocity of, I think it's 1/10 of the speed of light. So we need to actually give it a little bit less radius to give it a little bit more escape velocity. Now here, I think if I give it about like, what, 5 meters, and also maybe increase the mass a little bit more. Actually, it went the wrong way. I wanted it to increase, not decrease. Oh, look at that. Here we go. At 1% of mass of Sun, and also at 34 meters of radius, we get almost the escape velocity of the speed of light. And all of this implies that this is almost a black hole. Essentially, if I were to increase the density just a little bit more, it would become a black hole. And we can do this by, let's just increase the mass just a little bit more. And keep the radius where it is. And right around here. Yep. Okay, a little bit more. I mean, a little bit less. Here we go. 1 speed of light. So this is a Tesla Roadster black hole. Now, it doesn't look like one, mostly because the simulation doesn't really create a black hole out of human-made objects. But for all intents and purposes, this is a black hole. As a matter of fact, if I were to move it closer to its actual size, it would be an even more powerful black hole. The current escape velocity is way, way higher than the speed of light. It's like 3.4 times higher than the speed of light. We're not done here yet, though. We're going to keep increasing the mass of this object. And we're also going to keep... Ooh, okay, that's not exactly what I wanted. We're going to keep turning it closer and closer to an object that's going to become a supermassive destroyer of our solar system. So here, I think what I'm going to do is I'm going to give it 1 mass of the Sun. It is now a tremendously powerful, tremendously dense object that is going to start attracting pretty much everything from its vicinity toward itself. So if I were to zoom out here and take a look at the trails, you would probably see that very, very soon, pretty much everything is going to start moving toward us. Now, I think it already swallowed the Earth. I didn't really see how that happened because I think it just happened way too fast. But a lot of these objects will start moving toward us now. Let's keep increasing the mass of this. Let's make it 10 masses of the Sun to make it a little bit more realistic as a black hole. And we're going to also increase its size as well, because I want it to be a somewhat realistic looking black hole. And well, it turns out, as I was playing around with numbers, I basically completely changed the solar system, and now everything is out of whack, and here is the Sun basically flying toward us. Actually, it flew past us. Interesting. And I think a lot of other planets are also doing very, very interesting things. Now, my mission is not finished here yet. I actually, wow, look at the Mercury go. I wanted to see not just what happens if you turn Tesla into solar-sized black hole, but Also, what would happen if we essentially put it in the middle of the galaxy and then turn it into a large black hole as well? Now, this is kind of interesting. Look at what happened if I basically turn this into a black hole. No other collisions though, but things did kind of fly away and fly apart. Alright, so what I'm going to do now is I'm going to open this galactic simulation that actually has our sun right there in the middle. And we're going to place Tesla Roadster around it and once again increase its mass to the point where it can't really handle it anymore, just like it did in the last part. So this time though, we're going to go into like really large numbers. Right away, we're going to start with 1 mass of the sun and keep increasing it more and more and more. So right now the sun is actually in orbit around Tesla Roadster, but as things progress, it's going to acquire more and more mass of the sun and basically swallow the whole galaxy. Let's do this as 100 masses of the sun. And look at that, our spinning 100 mass sun Tesla Roadster is now going to be flying through the galaxy. Alright, so what I'm going to do is continuously increase its mass, and then we're going to observe the effects it has on the rest of the galaxy. And this time we're not going to worry too much about the actual radius, because it does seem to actually bug out the game sometimes. But we are going to increase its mass. And let's go into the thousands, while also increasing the speed of the simulation. So right now, this is actually what would be known as the medium-sized black hole, if it was a black hole, that is. Although it is technically not, so maybe we'll change its value so that it actually does become a black hole again. We'll increase the density just a little bit, but now I actually want to start increasing the mass even more. So at some point, also, I think it helps to increase the speed of the simulation a little bit, just so we can see stars moving around. At some point, things will start basically kind of clumping around the beautiful Tesla Roadster as it propels itself through the rest of the galaxy. So let's... Okay, there we go. This is beautiful. Look at that. We're flying through the galaxy. The simulation is right now at like 8,000 years per second. And so let's see what would actually happen to the rest of the galaxy if, by some unknown chance, the beautiful Elon Musk's Tesla Roadster became a supermassive black hole, much more massive than anything else we can imagine. So we're gonna go into the millions of mass of the sun. Right now it's about 25% the mass of the central supermassive black hole in the middle of Milky Way. And as this happens, you'll notice that, first of all, Sagittarius A is going to start moving toward us, and second of all, the other stars will start basically kind of moving around Tesla Roadster as well. And well, looks like even though I've increased the Tesla Roadster's mass to like ridiculous amounts, it still hasn't really done what I wanted it to do. Oh, maybe that's because it doesn't have the mass of the Milky Way yet. Let's do this. Yeah, there we go. Here we go. This is actually a little bit unrealistic because Sagittarius A Star is not as massive as the whole Milky Way. But in this simulation it is. So if I were to make it 4 times, if I were to make Tesla Roadster 4 times as massive as the Milky Way, then it would start attracting everything around it, right? There we go, look at that. It actually kicked out the Sagittarius A Star out of the system. And this is beautiful because this right here is what I wanted to create for a long time. Now this was completely by accident, but this kind of shows you how some this kind of shows you how some galaxies actually lose their black holes. Now we've found at least one, and I've actually talked about it in one of the videos that I've made previously, and you can check it out on the channel. But basically, this is exactly the simulation I've been looking for a long time. When a much more massive black hole approaches a smaller black hole, it can actually completely kick it out of the system, and then the galaxy, which is still there, basically starts kind of getting a little bit bumpier and bumpier. It's kind of hard for me to zoom into it now because it's so far away, but basically it sort of starts expanding and becomes more fluffy. And one of the biggest galaxies that we have discovered is actually that. It's a galaxy with no supermassive black hole, and it's the largest galaxy because it lost its central black hole through a collision with another galaxy. And beautiful Tesla Roadster, without knowing anything about the simulation, was able to actually recreate this very, very cool event completely by accident. Anyway, that's all I wanted to show you in this video. I wanted to play around with the Tesla Roadster, create a black hole out of it, and just so it happens, it actually was able to simulate a very, very cool event and show us how galaxies actually lose their black holes. Hello wonderful person, this is Anton, and in today's video we're going to be talking about a concept called hypercompact stellar system. This is an event that may occur when two galaxies collide and one of these supermassive black holes decides to escape and basically create its own fate somewhere else. Let's discuss this, recreate this, and look at it in Universe Sandbox, and welcome to What the Math. So a few billion years in the future, the Milky Way galaxy and the Andromeda galaxy will actually most likely collide. And when this happens, there's a slight chance that instead of the two supermassive black holes at our center, or basically in their center, combining into one, there is a chance that one of them will actually get kicked out of the system. And let me actually see if I can do it right now. We're going to try to change its velocity just a little bit to make this slightly more realistic and see if we can actually make it happen. And when this happens, and I actually was able to recreate this in one of the previous simulations where I did it completely by accident. It was actually a simulation where I used Elon Musk's Tesla and turned it into a black hole. And it just so happens that it kicked out the black hole from the center. And when the black hole got kicked out, it actually took a few stars with it and created what's known as a hypercompact stellar system. Now, obviously, when galaxies collide, sometimes they actually combine each other's black holes and become one. There's a chance that Milky Way and Andromeda will do the same. But we've actually observed galaxies that have no black holes, suggesting that two galaxies collided and the black hole basically ran away, flew away, and escaped and created its own system, which we're going to try to do again. Far, far, far away. So, okay, it's maybe not moving fast enough. I need to give it a little bit more velocity just so it moves faster. Let's give it maybe 2,000 kilometers per second. That should be enough. Now, what actually makes this sort of object different from, let's say, globular clusters? Well, for one, the stars moving around the hypercompact stellar system, also known as HCSS, is usually a type of a system where all of the stars move really fast. A globular cluster will have stars moving around it really slow, but here all of the stars move at like thousands or at least a few hundred kilometers per second. The other thing that makes this a little bit different from a typical object is that it's very massive. So a globular cluster would not really be that massive, but this, which is now technically a hypercompact stellar system, is ridiculously massive because of the black hole. And the stars here only represent about maybe like 1% of the mass, whereas the supermassive black hole is most of the mass. And so from a distance, it actually kind of looks like a very unusual, very weird dwarf galaxy or a globular cluster where everything moves really fast and there seems to be a lot of ridiculous mass. So there's actually a few of these we've discovered that we kind of suspect are these types of objects, also simply based on the amount of energy produced by the supermassive black hole. But we do think that this is kind of what may actually happen, or there's a chance that it may happen to our solar system, or not our solar system, but our galaxy, that is, the Milky Way. So there's a slight chance that the Milky Way black hole, also known as Sagittarius A Star, which I believe this is actually, I think this is Sagittarius A Star, might actually get kicked out of the galaxy and end up becoming this, which is HCSS. And interestingly, even though it gets kicked out of the galaxy, it still kind of remains in the same galactic cluster, meaning that it will probably even become a satellite of its own previous galaxy, and maybe at some point will escape further, but it will still be gravitationally tied to other galaxies that might be in the neighborhood. So, like for example, we can actually try to see if there's a smaller galaxy we can add. So kind of like this, I guess. Let's maybe make it binary. And so you will still have this cluster, also known as hypercompact stellar system, kind of orbiting in this vicinity. Okay, that actually unfortunately broke it apart. That's not what I expected to do. Well, anyway, so let's see if we can maybe create another one using. Well, no, let's use the same simulation. So we're gonna go with this simulation here, and take the supermassive black hole. Give it some velocity as it moves across the skies, maybe 3,000 kilometers per second, and let's see if we can create it again. Normally it's a little bit more difficult to create these because they're a little bit more unpredictable, but did we do it? Okay, something came out on the other side. You can see the black hole actually shot through the galaxy here, and I think I made it again. It might be in this vicinity. Let's check it out. Oh, there it is. Look at that, beautiful. I think I succeeded. Yeah, there it is. There's a black hole, and this is the new HCSS. So the thing about these particular objects is that we don't really know of actual examples just yet. So this is still kind of theoretical. We do have some suspicions about some of these objects being HCSSs, but we haven't really discovered them. But it's been estimated that nearby Fornax and Virgo galaxy clusters may contain hundreds or even thousands of these. So they're actually suspected to be quite common. They have been a lot of different clusters detected over the past few decades, and it's possible that we actually misidentified some of the globular clusters and some of the dwarf galaxies, which were in reality this thing. So it's possible that we need to reclassify these a little bit, because it's actually quite easy to find and quite easy to distinguish them by looking at them for a little bit longer than a few days, and you can kind of see that the speed around these things will be much higher than the speed around a typical globular cluster. So it's really about the compactness and the velocity of stars here. And also these will most likely produce a lot more flares, and they'll produce a lot more energy because stars here will probably approach the black holes, or the black hole in the middle, a lot more often. And so there will be a lot more outbursts of energy, and most importantly, a lot more different types of supernova. And the stars here would most likely be iron rich and very young. And so if we actually investigate a lot of globular clusters we discovered, we might find quite a few of these HCSS objects. And if we actually find one of these objects in real life, we'll most likely be able to then investigate and basically prove that, first of all, supermassive black holes may exist outside of the galaxies. Also, they'll help us predict gravitational waves a little bit more, and not just predict, but analyze gravitational waves a little bit more. And this would also imply that not all galaxies have supermassive black holes in their center, because some of them may have lost them over time. We have a few suspicions about a few galaxies, but we haven't really been able to prove it just yet. If we discover these with binary black holes or other unusual types of formations inside, this will help us understand how the universe evolved over time, and obviously help us understand how our galaxy was born and how we were created as well. Well, that's it for hypercompact stellar systems, also known as HCSS, and once we actually discover one, I'll make another video showcasing it and possibly recreating it a little bit better. Hello wonderful person, this is Anton, and in today's video we're going to explore a hypothetical scenario with our Earth being very, very close to the Sagittarius A Star, the supermassive black hole near the center of our galaxy. Welcome to What the Math. Ever since I watched Interstellar for the first time, the movie that I think would probably be in the top space movies I've ever seen, I always wondered, what would it be like to actually look into your skies and see a tremendously large supermassive black hole there? Unfortunately, in that particular movie, we don't get to see this very much, except for a few moments when they are in the outer space. But we don't really get to see what it's like from the actual planet. What is it like from the planetary surface to see such an unusual object? This is why we have Space Engine. In today's video, we're going to basically simulate this. We're going to take our planet Earth and relocate it temporarily right next to Sagittarius A Star. And in the video tomorrow, I'm going to show you how I did this as well. So first of all, if I go into my search box right now and I look for Earth, you'll notice that there's another Earth that I created called Earth 2. Jump to it and you find yourself right in the middle of the Milky Way. Now, the temperature here right now is minus 17 degrees Celsius, and this will actually change slightly when I move closer to the central area. But we are basically approximately 100 or so astronomical units away from Sagittarius A Star, which I think is this object right there, if I'm not mistaken. As you can see, the night skies here look completely different from the night skies on the planet Earth. And that's actually for one reason only. We have a lot more stars here. Because we are in the central globular cluster, there is a tremendous number of very, very bright stars. And because of this, they illuminate our planet Earth to the extent where it's actually acquiring this very different sort of a hue in its night sky, but also on the day side if there is one. Unfortunately for our planet right now, we don't have a star to orbit. In other words, this is kind of like a rogue planet. And we expect there to be quite a lot of rogue planets in this particular area of space. So this might be sort of a simulation of what some of these planets might look like. Now, I actually wanted to move a little bit closer to Sagittarius A Star. And so we're going to do this right now. Shift F2 to bring this menu up. And we're going to go and change the orbital parameters, which are right here. First of all, I want our planet to be much closer. Current distance is 89 AU. Let's go to maybe 4.5 or so. And if we just kind of turn around, we'll see the beauty of the black hole right there. Now, the interesting thing about this particular simulation is that I made sure that we actually have quite a high eccentricity as well. In other words, our planet is actually going to come very, very close to the central supermassive black hole. And also notice the temperature. We're now at 606 degrees Celsius. The tremendously powerful accretion disk that you see in the background is creating so much heat on the planet that it's basically going to get hotter and hotter the closer we move to the central black hole. Although I think we are maybe moving away. I'm not sure actually. Let's wait a little bit. We'll accelerate this just a little bit until our planet moves a little closer to the central black hole. I also want to actually decrease the luminosity a little bit because I want to be able to see the actual black hole itself. Alright, so it looks like we're now in orbit around the black hole, and you can see the planet even crosses the accretion disk. But the temperature here doesn't drop below about 500 degrees Celsius. As a matter of fact, right around here, the temperature goes into thousands of degrees, which is quite a lot higher than I imagined it would be. It's about 1200 degrees Celsius right now. So in other words, there's definitely not going to be any liquid water here. And probably no life either. Nevertheless though, I actually want to see what it looks like for us to stand right here in whatever bright object this is and look into the skies and basically see the actual black hole. So we're inside the atmosphere now, and this is kind of what it would look like for an observer standing on the planet Earth looking into the skies and basically seeing this tremendously humongous, tremendously powerful object right there. Now the thing is, because we're actually moving pretty fast right now, we're moving at several thousand kilometers per second, we would also start experiencing a little bit of the relativistic effects. In other words, time for us would actually move a little bit differently. And so right now I actually changed the time to real time, so this is what it would look like if you were to just kind of stand on the surface and to look around. Now, in one of the future videos this week, I actually want to create this as a 360-degree video as well, just so you can kind of see what this would feel like if you were to really look around and to actually look into the skies. But for now, we're just gonna have to go with the two-dimensional video I made right now. So anyway, that's what you'd see in the skies. And as you can see, there's a lot of dilation here. There's quite a lot of bending of light around the black hole. And obviously, as we cross the actual accretion disk, it's very likely that it would just burn everything on the surface completely. So surviving rate on the planet right now is pretty low, not very high at all. Now, before we finish the video though, I actually... Oh, look at that. Wow, this is going to be pretty amazing and pretty scary as well. But before we finish this video, I actually wanted to really take a look at something else. Oh, and look at this huge firewall approaching basically the location where we're standing right now as we advance time. This is actually quite terrifying. Just seeing this inevitable death approaching you from the skies. Anyway, so what I wanted to do before we finish this video is I actually wanted to place the planet much closer to the black hole and possibly even inside the black hole, and just to see what it might actually look like. But before that, let's actually just look for the last time at this incredible view of the central supermassive black hole Sagittarius A Star in our night skies. Alright. Let's do this. So what we're going to do is we're once again are going to bring up the editing box and change the orbital parameters to the point where our planet is actually now inside the black hole, or very close to the actual edge of the black hole, and that would be at a distance of about maybe 0.4 or so astronomical units. It's actually a little bit less than that, but this is pretty much the edge right here. And let's run this again. Let's actually see what it looks like if you are literally on the edge of the black hole. You can kind of see that this is pretty much as close as you can get before falling into it. The temperatures here are 3,300 degrees Celsius now. And as you can see, things actually start looking very weird. Alright, so I'm gonna run this a little bit longer just to see what happens. And I really wonder if we actually at some point are going to even enter the black hole. Oh, look at that. Yes, we did. We're right at the edge and almost inside the black hole. It's pretty crazy. So I just want to actually pause this and just to see what it looks like right from the outside. At this point, I don't even know where up it is anymore because the black hole actually bent the directions. It bent the light in such a way that, not just the light, the actual space-time, that I can't even see anything. Okay, so there is the surface of Earth. Very difficult to see now. And this is essentially imagining what it would be like if Earth actually entered the black hole. So right here, we're inside the black hole. Whereas right here, we're outside still. So pretty crazy. Definitely not a phenomenon you'd expect to experience in your lifetime. So anyway, so that's basically the edge of Event Horizon. And I think at some point it actually even enters, yeah, it definitely enters the black hole right around here. And obviously the part of Earth here would not be able to escape anymore. But because this is just a simulation, we'll be just fine. And yep, that's right. We're now inside the black hole. Well, actually, what I wanted to do is not this. I wanted to see if I can actually find a location here, somewhere around the black hole, where I can possibly place the planet Earth in such a location where we are... Oh, okay. I don't know what happened there. Oh, we're still inside the black hole. Oops. I'm trying to place it somewhere where we'll actually have a relatively comfortable condition for human life. In other words, something like 20 degrees Celsius. So let's see if we can do it. We're going to change the location, increasing the semi-major axis to maybe about somewhere around here. All right, so just under 81 astronomical units. So this is the best I could do manually. I can actually change this in the actual file to make it a little bit better. But this is a location where our Earth is actually receiving enough radiation to sustain relatively habitable conditions. Now, what this radiation is coming from is another story, because it's not actually infrared radiation in the same way we would get from our own sun. But nevertheless, at least in this particular simulation, we have now created what seems to be a relatively habitable conditions on the planet. Now, because there is definitely a lot of various rogue planets in this particular location of space in real life as well, it's quite possible that some of them are receiving enough various types of energy to actually warm up the surface enough to create some sort of unusual life-like conditions, and possibly even some exotic life. In other words, there is maybe a chance that somewhere around Sagittarius A Star, there is a lonely rogue planet, just like we have one right here, that actually has weird, unusual black hole-like life that was created here over what seems to be millions and possibly billions of years. Hello wonderful person, this is Anton, and in today's video we're going to be talking about TON 618, a quasar that seems to have the most massive black hole we have ever discovered in the middle of it. Let's discuss this a little bit more and simulate this using Universe Sandbox. Welcome to What the Math. So we're actually flying toward this black hole right now, and we're going to be going right in the middle of it at a distance of approximately 10.4 billion light years away, which also implies that this happened, or the light that we've seen from it, is about 10.4 billion years old. Now we're going to be actually not just looking at it, but we're going to try to place it right in the middle of our solar system and also very close to the sun, just to see how it influences both the planets and the stars near us. So this is what we're going to be doing. We're going to be basically taking a look at a tremendously massive black hole that's known as TON 618. Now we've actually discovered this black hole really long time ago. As a matter of fact, this was first seen back in 1970, and actually back then we didn't really still understand black holes or quasars very well, but it took many years for us to actually figure out that what we were seeing was essentially a galaxy whose black hole is so massive that it's producing so much light, and it's pointing that light toward us, that we're seeing it from a really far away distance. And so let's actually go to our own solar system right now and basically try to imagine how big and how tremendously massive this black hole is. So you can see Earth is right there, Sun is right here, and if I were to place our own Sagittarius A Star, which is the supermassive black hole, in the middle of our own galaxy, this is what it would actually look like. And we're going to basically go into the black holes and place Sagittarius A Star maybe right here next to Earth. So you can kind of see that's what Sagittarius A Star looks like, and it's approximately 4.3 million masses of our own sun. And if I were to just let go of the pause button right now, things would pretty much fall apart pretty quickly. Earth is already absorbed by the black hole, the sun will not really last very long, and the rest of the planets will be absorbed and turned into energy that's going to be released into some other faraway galaxy, similar to a faraway quasar that we're talking about today. So that's Sagittarius A Star. Now, the black hole that we're talking about, that was actually very recently studied, or I guess studied again, and only a few months ago we've actually been able to finally calculate relatively precisely its actual mass, is essentially now known as the most massive black hole. So let's go to the solar system one more time, and I'm going to show you how ridiculous this black hole is. So its mass is 66 billion masses of sun. That's essentially 15,000 times more than Sagittarius A Star. I'm gonna have to actually move away from our sun a little bit just so I can even place it somewhere where it doesn't actually destroy everything right away. We're going to go maybe at a distance of a few thousand astronomical units away from our solar system. So maybe somewhere right around here. I think this is probably a good location. And what we're going to do now is we're going to actually change the parameters to be more realistic, and you'll see that its size automatically changes right away because this game actually uses a lot of quite realistic physics formulas, and in this case it calculates the Schwarzschild radius very accurately. In other words, the radius where basically you reach the point where no light can escape anywhere. In this case, this radius is just over 1300 astronomical units. And this implies that this is basically the size of our solar system. So here, if I were to compare this to, let's say, the size of our own planet Earth, you would see that planet Earth is ridiculously tiny. It's almost impossible to see. Even our own sun would be actually impossible to see at this point. And, well, guess what's going to happen to our solar system if I once again let go of the pause button? So pretty much everything is going to start accelerating quite dramatically, and you can see the speed actually increases really fast toward Ton 618. Now this black hole is so massive and so large that some people don't actually think it might even theoretically exist. Some of the recent papers actually estimated we think maybe 50 billion masses of sun is the theoretical limit before the actual black hole starts falling apart into smaller pieces and create essentially other black holes or possibly even stellar remnants. But as of now, it seems that we can't really explain this any other way. The amount of light that this quasar produces, if you look at it from a distance, is essentially so dramatically high that the only explanation is that whatever's inside that galaxy far away is about 66 billion masses of our sun. So okay, we're gonna accelerate this a little bit just to see how long it takes for all of the objects to get this far. And let's actually maybe even take a look at our own solar system just to see what's happening there. So we're basically flying toward Ton 618. Oh yeah, it looks like everything is flying toward it ridiculously fast. As a matter of fact, you can see everything is kind of being unofficially spaghettified. As in everything is being stretched and pulled at tremendously powerfully to the point where things are moving away from each other at different velocities and different accelerations. So things are about to start colliding with the supermassive black hole here, so we're going to decelerate time just a little bit and see what happens. My guess is that everything's just going to get absorbed. Yep, there we go. Everything's gone now. It didn't take very long, just a few months for things to reach this particular point. But you can see that just the sheer size of this object means that if I were to place it right in the middle of our solar system, or in other words, if I were to change our sun into the size of this supermassive black hole, it would essentially look something like this. So here we go, I'm going to press enter and boom, everything just gets swallowed, and it's ridiculously large. Its size compared to everything else in our solar system would be approximately, so let me just take a simple object here. Let's take our Earth actually and measure the distance. So we're going to go away from the sun at a distance of about 1300 AU, which is somewhere right here. So that is how ridiculously large this black hole is. So about this big. That's basically probably one of the biggest objects that we've discovered that's essentially a single piece of mass that used to be something else probably. Now, I also wanted to see what would happen if we actually went ahead and placed this particular black hole somewhere in between stars. Like, let's just say we place it between our sun and Alpha Centauri, and this particular simulation actually shows you a relatively realistic representation of the nearby stellar systems. So here you can find all of the closest stars to us, including Sirius, Alpha Centauri, Proxima Centauri, and so on. So let's just take the black hole again and place it right there in between stars at a distance of about 2 light years away from our sun. We're going to let this go, and you'll see that within a few days, our sun will actually acquire ridiculously high speed. It's already moving toward this black hole at close to 20 kilometers per second. Now let's see what happens within the next few months, or maybe within a year. A year later, the sun is moving toward the star at 1,000 kilometers per second. And basically, it will only take it a few years to get to this object. So this black hole is pulling everything with such a high acceleration and with so much power that basically the entire system here will get, well, first of all, kind of destroyed, because stars will actually start behaving very differently. And you'll also notice something else happening very soon. It's very likely that it won't take very long before we start seeing the first supernova occurring, because some of these stars will start colliding with each other because they're all moving toward the same black hole, and at some point they'll actually just approach each other a little bit too close. Now let's see how many years it takes before our sun falls into the black hole. And here we go. It's actually moving toward the black hole very fast now, 50,000 kilometers per second. So basically we're starting to feel relativistic effects at this point. And it only took about 38 years for the sun to move, I guess about 3 light years to the location where Ton 618 was placed. And here we go. It's just going to probably get absorbed again. But in reality, what would happen is that the black hole would now actually acquire a tremendously large accretion field around it, or accretion disk. And a lot of the material would actually fall very close to the black hole and get spewed out as a kind of a projection from both sides, from the side up and down of the black hole. And this would actually create a tremendously powerful beam of light that would then be visible from really, really far away. So there come the supernova. The stars started colliding with each other already, and basically most of these stars will either collide with each other and create a lot of energy, but at some point pretty much everything here will actually fall inside the black hole. So this is how tremendously powerful and how tremendously large this black hole is. Now we will definitely not really see any other supermassive black holes of comparable size anytime soon, mostly because we don't actually even know if this is real yet. We think it's there, and we think it's kind of possible, but the theory behind the black hole mass limit tells us that maybe, just maybe, it's either several black holes or something else entirely that's causing this galaxy, this quasar, to produce so much energy. So Sean Raymond, the astrophysicist living in France, that has been posting really interesting blogs where he creates hypothetical solar systems and star systems, is at it again. He decided to create a hypothetical system with a black hole, a very, very massive, supermassive black hole at the center, that he then tried to add to his list of ultimate solar systems. And here he actually went as far as saying you can have up to 1 million planets in the habitable zone. Let's see how he did it. He took a supermassive black hole that's about 1 million masses of the sun, and he then started by placing a few suns around it. So he first placed the sun relatively close, and then realized that it just kind of sort of breaks down and turns into a ring because of the tidal effects. So that clearly didn't work, and he decided to place stars a little bit farther away. So for his next experiment, he took several suns, specifically I believe it was 9, and placed them in a relatively stable orbit at around 0.5 astronomical units away from the central black hole. I'm doing this very roughly here, so some of them might actually become kind of unstable, but it sort of looked like this. And here, if I actually make it run, this is what we'll see. So there's 9 stars, 9 suns around the central black hole, producing enough radiation to have a habitable zone at a distance. Oh wow, this is a lot brighter than I expected. At a distance that's about 3 times as far away as a normal habitable zone. In other words, it was at a distance of about 3 astronomical units. So starting from somewhere around here, there we go, 3 astronomical units, up to about 3 or maybe 4 astronomical units, you can actually have habitable planets, habitable Earth specifically. And because we're actually orbiting a supermassive black hole, the distance between these planets can also be much less than in his original system, where he had to place planets at a distance of about 12 Hill spheres, or just over 18 million kilometers away from each other. So in this system, you can actually have a single ring with up to, I believe, 4,200 planets. So you can have 4,200 planets right here. Now, I'm going to see if I can actually place that many. I don't think my computer can survive, but we'll try. So let's place one ring. And unfortunately, it's kind of hard to see it, but it's basically there. I think I can maybe select all of this. Yeah, there we go. There's that ring that represents those 4,000 planets, super tiny planets, that he basically tried to create hypothetically around this black hole. Now, the other thing is that you can have several rings here, and there's up to about 700 rings possible in this new habitable zone. So if you have 700 rings, 4,200 planets in each of them, that's close to about 3 million planets you can place in this hypothetical habitable zone around a central black hole. Now, all of this sounds wonderful, of course, but there's a lot of quirks to work out in this particular system. Well, and unfortunately, I won't be able to simulate this because my computer can't really handle this, but we'll try our best. So first of all, let's take a look at what's happening with our suns here. I think some of them are still falling apart. Yeah, so this is still not a stable region of space for these suns to be in. We need to place them a little bit farther away from the central black hole. So let's see if we can create suns. Okay, it kind of worked, but they once again fell apart, so I need to place them even farther. Even 0.6 astronomical units is creating a lot of tidal effects here, where the suns don't actually last very long. So let's start from scratch. We're going to place a 1 million mass black hole in the center. We now are going to also place 9 suns. So let's do this. 9 suns right here, with a total mass of, once again, 9 suns at a distance of about 1 astronomical unit, where I think they should be okay and won't fall apart. And we're also going to make this a ordered assignment. And let's try this. Okay, here we go. Here are these 9 suns in a very stable orbit around the black hole. These should not really fall apart. I think they will be pretty stable. Although, wait a second. Nope, my bad. They are also falling apart. The tidal effects here are really strong. This also means that it's going to be really hard for me to maintain the stability of the system, but let's just go with this for now. So there are the 9 suns, and now using the same technique, we can maybe place a few planets in the hypothetical habitable zone. So this is how we'll do it. Same thing, except that we're going to change this to, let's say, I don't know, like 30 planets. That are going to be 30 masses of Earth at a distance of about 4 AU, and there they are. So every moon here that you see is essentially an Earth-like planet with a mass of Earth. So we just need to go in here and change its composition to give it a little bit of water. And let's do one of them, just so that we can simulate what all of this will look like. So here is that moon. It's exceptionally bright because there's so many suns in the sky, and we're going to try to change it until it basically gets some liquid water on the surface here, which means that we might need to also give it a little bit of atmosphere just to see if this works. And it seems to have ice on the surface, but no liquid water. And that's probably because my suns actually fell apart and are not producing enough heat. So once again, we have to go to the planning stage and try this again. So far this is not working very well, unlike the blog post that he wrote where he simulated this with 0.5 astronomical units. I think even with 1 astronomical unit of distance for the suns, they won't really stay stable. They'll actually still fall apart. Let's try a slightly different scenario number 3 that he mentions in the post, which basically does the following. He takes a black hole, once again 1 million mass black hole, and places 36 suns farther away at a distance of about 6 AU, and here basically we're going to have our suns on the outside of the system, and this might actually be much more stable. And these are correct size, correct mass, they look like suns, so this should be slightly more stable. There's 36 of them, and on the inside here we'll place the actual planets at a distance of, well, I guess somewhere right here. So this is maybe about 4 to 5 AU. We're gonna place a bunch of Earths, because the actual habitable zone here looks very interesting. It's like a pattern that you don't really see very often. I'm going to place 2 rings here. One is going to be at a distance of about 4 AU with 42 planets, and one at a distance of about 5 AU with about the same number of planets. Oh, and I also want to add another layer at 3 AU, and let's just actually add one at 2 AU and one at 1 AU, because I really just want to compare these in terms of the temperature they receive and in terms of everything else that might be happening here. And so let's see what we've actually created here. So we have stars on the outside, we have planets on the inside, and basically 1, 2, 3, 4, 5 layers. The first 2 layers here, the temperature is a little bit too high, even though according to the simulation they should be just outside of the habitable zone. The reality is that because there's so many stars here, the first 2 layers basically make it uninhabitable, too hot. Even the third layer, assuming that there is actually some atmosphere, so let's give it some atmosphere to see what happens, would most likely create unlivable conditions and make it way too hot yet again. So as soon as we add some atmosphere, the greenhouse effect basically puts it sort of in the unlivable conditions again. Too hot. What about this next layer? This is at a distance of 2 AU from the black hole, and here things get a little bit more interesting. So here we can actually maybe create something that's going to be very similar to Earth, and we might be able to even terraform this moon. Now currently it looks very strange. I think it's actually filled with water or something else. I'm not entirely sure what this layer is on top here, but we are going to give it some water because we want it to be a world with liquid water. And it looks like, yeah, it looks like it got liquid water, but it's once again a little bit too hot. The temperature here is 42 degrees Celsius already, mostly because of the atmosphere I've given it. And the last layer at 1 AU from the black hole, which is right here, is probably the layer where we can create habitable planets. So this is actually the habitable zone that Sean Raymond tried to create as well. And here with basically just a little bit of atmosphere and relatively similar conditions to Earth, the temperature is still pretty high. It's actually still climbing. Now, why is this happening? Well, I think one of the reasons is the same reason why we can't really see the surface here, because the stars are shining at this planet from all directions. In other words, there is never a night on this planet. There's almost no way for it to cool down, and it's constantly being bombarded by radiation from all directions. So this planet has no night, no way to cool down, it's always getting hotter, and is basically increasing in temperature. I might be able to place it a little bit closer to the black hole and eliminate this, maybe making it a little bit cooler, but I don't think it's going to survive there due to the tidal effects. The other thing about this particular planet is that it's currently moving at a speed of about 1/10 of the speed of light. In other words, it actually is getting some dilation effects. The time on this planet moves slightly slower than it does on normal Earth. And if you were to do the calculations, you would discover that for every 100 years, you actually basically lose about 2 months of your life. Now, it's not a super big time dilation, but it's still measurable enough. But because we're moving at 10% of the speed of light, which is a pretty high speed, it means that we cannot actually easily escape this orbit. We can escape the planet, but we'll never be able to go to other planets here. We'll never be able to leave the system because we'll need ridiculously high speeds for us to actually change orbits. And lastly, and this is probably the biggest problem in the system, the tidal effects. The tidal effects here are so high, which doesn't really show you much here, but they're so much higher than they are on Earth that you would constantly have tsunamis, earthquakes, volcano eruptions, and a lot of other problems here that Earth doesn't experience as much. And eventually this planet might even start falling apart, unless it's tidally locked. And if it is tidally locked, it would actually be stretched quite dramatically and would be pointing toward the black hole and would also spin way too fast. Which of course could give it a higher magnetosphere, but also possibly create some other problems that I'm not really able to think of right now. And a single orbit here takes something like 8 hours or 9 hours around this black hole, meaning that a year here lasts for 9 hours. There's never a night, so the seasons and the day-night cycle is completely out of whack and really, really difficult to imagine and also to survive on this particular object. I wanted to actually place Earth here just to see how it fares with these conditions. And once again, Earth for some reason got the same effects as the other planets did. But in terms of climate, let's see if anything actually changes here. So we're going to give it some time to adjust itself. And let's see what happens to temperature. And as you can see, yeah, temperature started skyrocketing almost right away. So that means that even Earth in this particular situation would not be dealing with these conditions very well. As you can see, it orbits around the black hole really fast. It's receiving sunlight from pretty much every direction. There's never night, there's never any season. It's just one super hot conditions here. So in between the constant heat, the tidal effects, the fact that there's time dilation, and possibly also the fact that a single asteroid coming from the outskirts here, colliding with the planet, would most likely destroy the entire planet, means that this is not really the habitable conditions we would want to have. Basically, if something comes from the outside of the black hole and then collides with one of these planets, it will most likely be colliding with them at relativistic speeds. So like even at 0.1 light speeds, let's just try with this moon number 14, at 0.1 light speeds, an asteroid would most likely create a tremendously large disaster on the surface here, and any kind of a tiny asteroid would still produce enough energy to constantly heat up the atmosphere to the point where this planet would be always ultra hot. There's a lot of things here that are not really as easy to imagine as they would be on a normal planet, and as you can see, this tiny asteroid that I just collided completely destroyed this planet almost instantly. So definitely not a place where we can easily have a so-called habitable zone. Now, all in all, these scenarios are definitely fun to read and to imagine, and this would probably make a pretty cool science fiction book, but the science behind this is so complex and there are so many factors involved that just kind of saying that I can place 1 million planets in a habitable zone around a black hole without any concerns and any potential issues is just not that simple. So you do need to actually take a lot of these things into consideration. Other than that though, this is actually kind of cool that you can create these in Universe Sandbox, and I would actually even like to maybe recreate some of this stuff in Space Engine just to see what it really looks like. Because in this simulation, if you were to actually place millions of planets together, they would be really close to each other, and a single planet would be only approximately 30 to 40,000 kilometers away from each other. In other words, you would always have these really large planets in your night skies, about 40 times the size of the moon. And this would be a pretty awesome thing to imagine. So maybe we'll try this in Space Engine sometime in the future.